Okay, guys, so let's talk about the actual mechanisms or how a reaction takes place. Now, we are used to regular chemical equations, right? So I'm gonna give you a sample chemical equation. You don't need to write it down, but something like this, right? This is what we are familiar with looking at. Now, these chemical equations, even though they tell us very valuable information like the mole ratio, what chemicals are involved, it does not tell us how the molecules react together, like what they actually do. Okay. Now, in this section, we're going to be talking about how these reactions actually take place. Now, some of them take place in a single step. So we got an equation right here, or so a chemical reaction right here. And it takes place in one step where the N and the C basically rotates and the C bonds with the other C. Okay. Now, these steps that take place in a reaction happening, it's called an elementary step. Okay. So you might want to jot that down. An elementary step is basically what happens in the actual reaction in one step. Okay. So that's an elementary step. It's basically the most, I guess, basic thing that happens. The molecules have to do the most basic thing the molecules have to do in order for a reaction to take place. Okay. Okay, so depending on the chemical reaction, these molecules move they can move in multiple steps. Okay, so depending on how many steps it takes for a reaction to take place, we define the equation by its molecularity. Okay, so basically the molecularity tells you how many steps it takes for a reaction to happen. Okay, how many basically things the molecules need to do in order to complete the reaction. Yes.
Were those the numbers that we were talking about in before? It was like 0, 1.
No, that's reaction order. Yeah, reaction order tells you how the concentration changes. This is actually talking about how many how many different times the molecules move in order for a reaction to happen. Yeah, completely different. Okay, so if a reaction can take place in one step, it's called unimolecular, right? Which makes sense. Uni stands for one, prefix for one. If a reaction requires 2 steps, it's bimolecular. If it takes place in 3 steps, it's termolecular, so on and so forth. Okay. Okay, now I'm gonna draw an amazing picture for you guys, as you guys are used to. Okay, so let me talk about what unimolecular, bimolecular, and termolecular means, okay? So unimolecular basically means there is one molecule, okay? This is uni, okay? And inside the molecule, something happens, and then the reaction completes. That's unimolecular, okay? When there's only one reactant. Okay, basically the one reactant does something to itself and it completes the reaction. Okay. Let me like this example right here, the one we just saw. If you take a look at this, it's one molecule, right? And then it just switched, the C and the N switch place, but it's still within the same molecule, right? There's only one reactant. This is a unimolecular reaction. Okay, where one thing changes within the molecule. Okay, bimolecular is when you have 2 reactants and then they collide with one another in the correct way, and then they complete the reaction. This is bimolecular. Okay, so there has to be 2 molecules colliding. And this is within the same elementary step. Okay, and then a termolecular reaction is where 3 very specific molecules need to collide together at the same time in the correct orientation, and then the step takes place. So this is very rare, and that's why we usually don't see things like tetra or pentamolecular, because it's already such a low chance of 3 specific molecules hitting each other with the specific energy in the specific orientation. It's already very difficult for 3 to collide at the same time. So usually 4 and 5 doesn't really happen. Okay, so it's going to be always uni, bi, or ter. Okay, I mean theoretically it could, right? But theoretically you guys could pass this class, and theoretically I could be a nice person, but unlikely. So
Does the molecularity
Mhm.
does the molecularity affect the reaction speed by just
yes,
higher?
yes,
Okay.
yeah. So term molecular will be a lot slower because the chances of that happening is very low, and yeah. Good question. Okay, so make sense what uni, bi, and term molecular mean? Okay. Okay, so we have some examples right here. Of what is it? The elementary reaction with the rate law and the molecularity. Okay. So in this reaction, if you guys notice, there are 1, 2, and 3 reactants, right? There's 1A and 2 Bs. Now, since there's 3 different molecules, even though there's 2 Bs, there's still 3 separate molecules that have to react at the same time. This is a termolecular step. Okay, does that make sense? There are 2 different types of molecules, but there are still 3 individual molecules that need to react. So this is termolecular. Okay. Another example right here. There are 3 A's, but it's 3 separate molecules that need to collide at the same time. So this is still termolecular, even though there's 1 type of reactant. There's 3 individual. Okay, this right here, O3 and Cl, this is bimolecular because there are 2 molecules that need to collide. And then this right here will be bimolecular because if you look at the rate law, wait, why is this bimolecular? Am I tripping? Why did I write that? This should be ter. Sorry, guys. My fault. This is termolecular. Off me, yeah, go ahead.
Wait, so if it's 2NO, so the nitrogen, whatever is balanced, are they like colliding like as one molecule?
No, they're 2 separate NOs. Yeah.
No, but I'm saying like NO itself would be colliding as a single molecule, and then you have a different NO. It's not would be you not have a nitrogen and an oxygen try to collide at the same time, and then a different nitrogen and oxygen collide, and then hydrogen.
You lost me after you said collide like 5 times.
But we're using like instead of using hydrogen molecule, we're using like a nitron side. Like that's.
So are you saying it's an NO colliding with a H2 and they're separate NO?
Yeah. No, would it be a separate would the nitrogen be separate than oxygen, or would it just be?
No, it's still they're combined. Yeah, it's 1 molecule. Yeah, I think I just made a typo right there. Okay. Yeah.
So I'm confused what like an elementary step is.
Uh-huh.
Because like, is that like when it's only 1 step? Because, so when it says like elementary reaction, is that different than elementary step?
An elementary reaction is a reaction that takes place with just one of those one elementary step. We're gonna get into ones where there are multiple elementary steps that take place, but we're not there yet.
How can it be like termolecular and bimolecular, but also?
Yeah, the 1 step is the 3 things colliding at one time. That's the step that it needs to happen. It's like 1 event. An elementary step is a reaction that takes place in 1 event. And the 1 event for a bimolecular is 2 things colliding. That's your event. So this is your elementary step. A termolecular is when 3 things collide together, and that is your 1 event. So that's an elementary step. It's 1 event that has to take place for a reaction to complete. Later, we'll get into reactions where 2 events have to happen, and then the reaction takes place. That makes sense? Yeah.
So reactions like other steps.
Yes, it could be multiple elementary steps. It could, because things can just shift around. Right now, we have very small molecules, but things that are like large structures, like multiple things can happen inside the structure. Yeah. And Sammy, did you have a question? Okay, for sure. Yeah, I know this is getting very confusing. So let me just clarify before we move on. An elementary step is like an event. Basically, something happens between molecules or within a molecule. And then the molecularity tells you how many molecules are involved in that step. Okay, unimolecular means that only one molecule is involved in that step. Bimolecular means 2 molecules are involved in that step. And termolecular is when 3 molecules are involved in that step. But it's still all within one event.
And basically what we've been learning for like the past year is just elementary reactions.
No, not necessarily. We haven't been talking about how many steps elementary steps there are in
Yeah,
the
but
reaction.
it's just like single reaction is one.
No, not necessarily. There can be multiple elementary steps in a reaction.
Oh,
Remember the chemical equation that we look at normally? That doesn't tell you anything about how many elementary steps are in that reaction.
Oh, I thought each like equation was just one step.
Yeah. What's up?
Just a single step.
Yeah. The molecularly applies to one of the steps.
So it's related to
Exactly, yeah. But it doesn't tell you how many steps there are in a reaction. Yeah, or you'll usually be told. Yeah. So,
so like that first example reaction, like at the top, yeah, that one. So like what part is made of elementary step? Is that whole thing, like this one elementary step?
yeah, this is one elementary step.
It's showing it like spread out.
Yeah, it's showing you what it would look like. Like this would be remember in our the reaction mechanism?
Yeah.
That would be the activated complex, the highest point, the transition state. That's what this middle one is. This is the start, transition step, and then the end of the elementary step. Yeah. Okay. Any other questions? Okay. Trying to think of an analogy to help you guys understand.
You don't.
Actually, I have one. Let me give you guys one. So, okay.
It's about relationships again.
No, it's not. It's about cars again. Okay, so if when we look at a chemical reaction, right? Let's just say that in a chemical reaction, it'll tell you that, hey, there were 3 cars. Okay. But then at the end of the reaction, I don't know. This car was bumped into this car, and then this car bumped into this car like that. Okay, so that's the chemical equation. Okay, this is the reactant, this is the starting point, and this is the ending point. Okay, now a chemical equation does not tell you how you got to that ending point, right? You just know at the very end, these 3 cars were collided together. Make sense? Okay, but different things can happen in order for this reaction to finish up. And the different events that take place, those are the elementary steps. So for example, within this equation, it could be like this. So this red car was driving. And then the first event could be that the blue car all of a sudden like spun sideways. Okay, just by itself. Okay, in that event, there was only one car involved, right? So this first step would be unimolecular. Okay, so far so good. Okay, and then after that, the next step could be, because the blue car spun sideways by itself, the red car hits the blue car. Okay, that's another step that took place. This would be bimolecular because there were 2 cars involved, right? And then the third step could be, now that these 2 are one thing, the black car comes from the side and hits the blue car. Okay, that would be, you can, I guess, argue if it would be either bi or termolecular. Okay, let's just say it's bimolecular though. This would be a bimolecular elementary step, and then we get to the end point. So this original equation only tells us what things were like in the beginning and what things are like at the end. But there could be multiple steps that take place in order for you to get to the end point. And those are elementary steps. And then depending on how many cars were involved in each step, that tells you the molecularity. Does that kind of help? You understand it? Yeah. Yeah, it's a car crash. Yeah. I guess we could have made this about dating too, but. Oh, dang, man. I thought of the dating one now. Yeah.
We have time.
Okay, sure.
Why is the last one by?
I guess you could argue that it's tri because the three still need to be involved, but these are already collided together, so they're stuck. Yeah. Yeah. No, I'm not gonna give the dating one. All right.
No, please. We love the dating one.
Okay, fine.
Yes.
I'll give you the dating one. Okay. All right. So I'm gonna pick some random names. Okay. So at the beginning of this whole saga, okay, you got Bob. You got. I gotta think of names of people who aren't here. We got Jim. And then for the lady name, or some we got Jenny. We don't have a Jenny in here. What is one? And then we got Sue. We don't have a Sue, right? Okay, so this is the beginning, okay? And then at the very end, we're gonna assume that Bob and Jenny got together. Okay. Okay, Bob and Jenny got together. And then at the very end, Jim and Sue are still alone. Okay. Now we know what happens at the beginning, right? And we know what happens at the end, but we don't know the steps that took place for this to happen. Okay. Now each event is a elementary reaction. Okay. So let's just say first, okay. Ooh, gotta keep it color coded. Okay. Let's just say that the first step was Bob and Sue got together. Okay. This is a bimolecular step. Okay. So far, so good. Now they are one molecule because they're in a relationship. They're an item. Okay. And then on the side, we have Jim and Jenny. Okay. Now the next step could be Bob and Sue break up. I know. And now we're back to, I don't know. Okay. And this is unimolecular because they were one item and now they broke up, right? And then the next step could be, okay, let's just say that Bob is here. And then Sue and Jenny both went for Bob again. Poor Jim. Nobody wants Jim. Okay, this will be termolecular. Okay, and so Bob is talking to both of them at the same time. But then at the very end, he decides, no, I'm not gonna get back together with Sue. And then he just goes stay with Jenny. And that's your last elementary step.
So it's like the original version is like watching the first 10 minutes and then the last 10 minutes.
Yes,
is, like,
exactly. Yeah.
You don't like get any of like the drama that happens.
Yeah. And then the elementary steps tell you the drama and the molecularity explains what happens in each of the scenes. Drama. For sure. I'm glad. Do you have a question? Oh, okay, for sure. All right. We spent way too much time talking about that. Too many analogies. So let's move on. Okay. So for 11.18, I want you guys to take a look at this equation. Assume that it's one elementary step. I want you to write the molecularity and the rate law. Okay, this should be a pretty quick problem. Law. Okay, so let's start with molecularity. Should be pretty simple. If this is just one elementary step, what's the molecularity? Bi, yeah, it's 2. Yeah, so 2, so which means it's bi because there's only 2 molecules that are involved. And then for the rate law, we can write that the rate is equal to the constant. There's only 2 reactants, so NO and Cl2. And since we aren't told the order, we can just assume it's the coefficient. So it should be 1 and 1. Okay. So if you are told the order of the reaction, then yeah, you can put in different exponents. But if not, you can assume that it's just the coefficients. Okay. Yes. Yeah. The exponents. Yeah. M and N. Okay, so that's one step reactions. Unfortunately, it's too easy. And we respect you too much as an organization to give you one step reaction. Okay. Now, no, I have to respect you. Okay, so the questions are usually going to be about multi-step mechanisms. Okay, so reactions that take place over multiple elementary steps. So like the examples we were talking about, there's going to be things that happen before the end of the movie. Okay. So some reactions, they have multiple elementary steps and they add up to an overall reaction. So you're going to be given the overall reaction. So this is a reaction that takes place overall. Okay. But it's going to take place over the course of these 2 steps. So in the first step, if you guys notice, there are 2 BRCLs, right? one of the H2s and one of the BRCLs are going to react to form these two compounds. Okay, now before we move on, what's the molecularity of this step? Yeah, it's bimolecular. There's only two molecules involved, okay? Okay, and they're gonna form HBr and HCl. Now, one of the HBRs that was formed is gonna react with the other, because remember there are two BRCLs, right? It's gonna react with the other one in order to get your final two products. So what is the molecularity of this step? Bi. So they're both bimolecular steps, but the overall reaction where two different HCl's are formed and a Br2 is formed is gonna take place over the course of two steps. Those are the steps that take place in order for the reaction to finish. Okay. Yes.
Is there even a way to figure out the steps?
No, it's all experimental. Yeah. And so you will never be asked to write the elementary steps unless you get like a substantial amount of information about the reaction. Yeah.
Or if they say it's like a single.
Yeah. Something like that. Yeah.
Chart on the page above.
Uh-huh.
So the curriculum at the bottom one is molecular.
Mhm.
It's because there's two mold, I know that one will H2, or is it because then grateful? I know it's because it's two is N.
It's because of the elementary reaction right here. There's two NOs and one H2. Yeah, there's three molecules that need to collide in order for the reaction to take place.
If we talk about the like exceptions to the coefficients, like how it's usually the coefficient is the
Yeah. It's not the coefficient when it tells you.
Okay.
Yeah, it gives you the rate order. Yeah. Okay. So if you guys notice, since there are two different steps that take place, right? Each of the steps have their own rate law. Okay. So every single elementary step has its own rate law describing that step. Okay. Now, if you guys notice, in the overall reaction, which of the compounds that you see in the steps is absent from the overall reaction? Yeah, HBr. So you see HBr in the steps, but it doesn't make it into the final equation, right? Because it forms and then it reacts again and it disappears. So compounds that are formed in one elementary step and then used in the next one, those are called intermediates, okay? They get used and abused and then they disappear and nobody remembers them, okay? So HBr is an intermediate because it gets formed in the reaction, but then it gets used by the other compound to make the other products, okay? That's an intermediate. And then we have our, what is it? Our energy diagram for what the intermediates would look like, okay? So this right here will be step one. The reaction or the reactants for this one will be H2 and 2 BRCLs. So we have H2 and then we have BRCL 2 times. Okay, H2 and BRCL would react together to form, sorry, I forgot the reactions. HBr and HCl. So here we make HBr and HCl. And then the intermediate would be HBr. No, you just gotta be able to identify like, so if they give you the multiple steps and give you this energy diagram, they would just ask you what's the intermediate, and you'd be able to identify that. So this would be the two intermediate steps. And then step 2 would have to happen right here. That's gonna be another transition step. And then you'll end up with your two products, which are H2 HCl's and Br2. Yes. So it's not an intermediate because it ends up as a final product. I just put it here to show that this is what's formed in this intermediate step. Yeah. But HCl itself is not an intermediate. Yeah. So whatever is in the overall equation, that is not an intermediate. Okay.
It's like the amount of steps.
Yes, exactly. Yeah, each of these peaks, that tells you how many steps there are. Because every time an elementary step takes place, it needs to overcome another energy barrier. It's getting very complicated now, right? Like I said, I don't like this unit. All right, let's, do you guys still need this? Anybody still copying anything down? Okay, let's go to 11.19. Here, I'll just take a picture. Okay, 11.19. So we have an equation here. Now, I'm gonna just tell you right off the bat that these are the two steps. Okay, so this is step 1. This is step 2. Okay, now for part A, I want you guys to describe the molecularity of each elementary step or reaction in the mechanism. So give me the molecularity for 1, give me the molecularity for 2, and then I want you to write the overall reaction and then identify the intermediates. Okay, so it's kind of combining everything we just learned this class session. So try that out, and then we'll move on to more stuff about this. Okay, so let's start with part A, because I think that's the easiest. Let's figure out the molecularity. So if you take a look at step 1, how many molecules start the reaction? Just 1, right? It's just O3. So this is unimolecular. Okay. If you take a look at step 2, how many molecules start the reaction? 2. So this is bimolecular. Okay. Basically, you just need to look at how many individual molecules are involved in the reactant side. Okay. All right. Part B is the one that I think it can start getting a little bit tricky. So let's start going over it. So easiest way, I think, to figure out the overall equation is you want to take a look at what's on the reactant side, what's on the product side, and cancel out whatever's on both sides. Okay. So if you take a look at this equation, it's basically saying that O3 is going to split up into O2 and O. Okay. And then in step 2, another O3 comes along and bumps into the O and makes two different oxygen molecules. Okay, so if you take a look at this reaction, what is the compound that gets used up basically? Yeah, O. So that's your answer to part C. The intermediate is just O. It's me. I'm used and abused by you guys. Okay, so I've never abused you, ever. Never emotionally, verbally, academically, never done that. Okay, so you know what? You be quiet, okay? All right, so if you take a look at this reaction, it's basically you make O and it gets used up. So basically O is used up in the reaction. So how many O3s did you need to start? Yeah, you needed 2 separate ozone molecules, and then they turn into how many oxygens? 3. And so this is your overall reaction. What happens in the reaction is an O is created and then used by the other O3. Okay.
Because the one I had like didn't make any sense. Like,
Yeah. So do you guys remember Hess's law from thermodynamics?
Yeah, a little bit.
Where you cancel out the reactants and product? Same thing. It's the same principle. Yeah.
Um,
I'm pretty sure you'll get partial credit because there's still 3, but yeah, I would take off points because you need to put them together. Yeah, good question though. All right. Make sense? Hopefully that helps a bit. Okay, guys. Okay, so now we've talked about the elementary steps. We've been talking about rates, right? We're going to incorporate rates into it. Okay, so basically, now every single one of these steps goes at its own rate. Okay, they have their own speed. I know they're gonna turn into stupid long problems. So, like Sammy pointed out, remember how there's these humps, right? That's the individual steps. Now, if you guys notice, they all have their own heights for the energy barriers, right? So depending on the height, it tells you how quickly or how slowly that step takes place. And we're gonna have to take those things into account. Okay, so basically, one easy way I think there is to understand this concept is that, let's say this reaction is traffic, okay? So this side right here is your reactants, and this side right here is the products, okay? And in a reaction, you're trying to get from point A to point B, okay? But on the way, there are these toll booths, these toll plazas, and we all know, if you've ever been in a car, that when you start getting to a toll booth, what happens? It slows down, okay? Now, so this is going to represent the steps that need to take place, okay? So this will be step 1, This is step 2, and that finally lets you get to the product. Okay. Now, depending on the rate at which traffic goes through each of these steps determines the overall rate of the reaction, right? Because even if everybody is going super duper fast, if it slows down at one point, it's going to slow down the entire flow of traffic, right? So basically, depending on which step slows down the reaction the most, that is the one that's going to determine the rate of the reaction. That's called the rate determining step. Okay.
So it's like it's link in the chain.
Weakest link in the chain. I actually think about this when I drive all the time. When you're driving and there's one really slow car in front of you, everyone's trying to go fast, right? But we can't go fast because there's one super slow car in front. I'm like, dude, this is the rate determining step. I actually think this. Okay, so the rate determining step is the car that slows down everybody else. Okay, you could think of it as a group project. You got the rate determining step in every group, right? The one person who is extremely slow, doesn't do any work. Allison, stop looking at him. But there's always one person that slows down everybody, right? And that's the rate determining step in a reaction. Whatever step slows down all the other steps, that is the rate determining step. That's the one that's going to overall determine the rate of the reaction. Okay, guys, stop accusing each other of being the rate determining step. I did not teach you guys this so you can accuse each other and insult each other in other classes where other teachers don't understand
I
this.
mean, I kind of get this, but I could really use like an analogy of like a certain situation.
Okay, Robbie.
Okay.
I'm trying to go home. You are the rate determining step of that process, okay?
It's the same time every day, no matter what.
You know, you're the next rate determining step. All right, let's move on. Okay, so let's go back to the problem, that reaction we were looking at earlier. Okay, there are 2 steps, right? And then let's just say that step 1 is the rate determining step. It is the slowest step. That means the rate of the overall reaction is going to be the same rate as the slowest step. Okay, so let me repeat that. If we only look at the overall reaction, right, you would write, hey, the rate is K, and then the reactants, H2, and then BrCl, right? This is how we would originally write the rate law for this reaction. However, since this step right here slows down the entire reaction, that means the rate of the overall reaction is equal to the rate law of the slowest step. Okay, the slowest step determines the rate for the entire reaction. Make sense? Yeah. It'll tell you. Yeah, or it'll give you the numbers and you can just determine it. Yeah.
Why wouldn't it be like an average of the 2 rates?
Because, okay, like, remember, it's like it's the example with the toll booths. Okay, like if it slows it down on one of the toll booths, it's not going to be the average. The average isn't going to be the entire. The flow of traffic is not going to be determined by the average of the speeds that you go through. That slow toll booth is going to slow everything down. And you know how only like a couple cars go out at a time if it gets slowed down? This thing right here determines that rate. So even if those cars, after they get through the toll booth, go really fast, the rate of the entire overall journey is going to be dependent on this one stop. Same thing with the reaction. It's going to be dependent on this thing. This thing slows down everything. So you won't have enough reactants here, even though this is a fast step, right? You're not going to have enough reactants here because they get made so slowly. So this step also gets slowed down, even though it could go fast.
Oh wait, so like it's like that one is only being about at a certain pace, that reaction can only happen at the
Exactly,
pace of the other
exactly. Yeah,
Okay.
that's probably a better way to describe it. Yeah.
Wait, so like
What's up?
you know the like supply connection where like supply is going slow and then Fubo is like speeding
Mm-hmm.
to
Yeah.
every, like, but they still can't go.
Yeah, exactly.
Stoplight, so it's not the average, it's like, it doesn't matter. the
Exactly.
speed.
Yeah. Mhm. Yeah. The rate determining step just slows down everything. And so even though the second step could go fast, it gets slowed down because it's not supplied the reactants in order to finish up. Yeah. Make sense?
So they would give you the slowest.
Yeah, they'll either tell you explicitly this is the slow step or give you the numbers And then you'll be able to determine based on the numbers that it's a slow step. Okay. All right. Make sense? You guys ready to do problems with this?
Why would they just give you like, that's just-
Yeah, so it's because you can't determine this like just by looking at the reaction. You have to experimentally. So again, they'll either tell you, so I'll actually give you the example to show you. They'll either tell you it's slow, like which one's slow or which one's fast, or it'll tell you the rate. So like they might be like, hey, this guy's rate is 0.5 molarity per second, and this guy's rate is, I don't know, 2 molarity per second. And then you'll be able to determine which one's slower and which one's faster. Yeah, one or the other. Okay, with that being said, let's go on to 11.20. I want you guys to write the equation for the overall reaction, same thing as before, and I want you to write the rate law for the overall reaction. Okay. Hopefully this isn't too bad. Just take a look at the example above. If this is a little confusing, I'll show you how to do it. Okay, so let's write the equation for the overall reaction. Now, all we gotta do is figure out the intermediate. What's the intermediate? Oh yeah, it's me again. Darn. Used and abused as usual. Okay, so you can eliminate the intermediates, and that's gonna let you write the overall reaction. We're gonna write N2O. How many nitrogen dioxides do we have? 2. Yep. And then do we have any other reactants?
No.
Oh, so yeah, 2 nitrogens for the product, and then the last one is O2. So this is the overall reaction. Yeah.
You just put in simple problems or you're the intermediates, you just say.
Maybe I thought of that, or maybe it's a happy coincidence. Who knows?
Is it always like O or is it?
No, it can be anything. Like I think the previous example that we looked at, it was like BR or HBR or something, right? Yeah, it was HBR. That one's not me. Hubber. Okay, let's go to the rate law. Now, it might be tempting to just get the overall reaction and be like, hey, the rate is equal to K N2O squared. But that's incorrect because we know what the slow step in the reaction is, right? So that means that the rate is actually K and then it's just N2O. So this is your rate law.
So, it would just be K.
N2O, yeah.
No, two. Wait, why not?
Because the slow step determines the rate of the reaction. Yeah, the rate law for the overall reaction will be equal to the rate law of the slowest step.
So it'll always be
Mhm.
slow.
Yeah.
So this is be the rate law of the overall.
Exactly, yeah. So there's 2 nitrogen dioxides, right? The other one doesn't matter. It's only the first one that matters. It depends on how quickly N2O can decompose into the 2. It doesn't matter that there's 2 of them or anything like that, yeah. Exactly, yeah. So yeah, your rate law is going to be the slow step. Just remember, the slow slows down the whole reaction. Okay, just like the slow person in your group slows down the entire group project. Okay, because no matter how fast the rest of you guys do the project, that slow person keeps you from finishing. Okay, doesn't matter how fast you are. If they're slow, it doesn't work. All right, so let's try a problem that's a little bit trickier. We're gonna go into this one right here, okay? So we got an overall reaction and you have the 2 steps. Okay, it tells you the experimental rate law. So they did an experiment and found the rate law. I want you guys to describe what that says about the steps. Okay. Okay, so if you guys take a look at the experimental rate law, which step's rate law is this? The first step. So what does that tell you about the first step? Yeah, this is the slow one. This is the one that is slow. Okay, and so this is the faster rate. Okay, so what you can basically say is that, hey, the experimental rate law is the same rate law as the first steps. Therefore, this one is the slow or the rates determining step, if you want to get fancy schmancy.
It's like rate determining or rate step better.
Both are same. Yeah. Okay, let's move on. I think this is the second to last section. Oh my gosh, we're almost at the end. Okay, I mentioned at the very beginning of the unit that one of the things that also determines the rate of a reaction is something called the catalyst. Okay, now you guys might be familiar with this term, but catalysts are basically compounds that interact with the reactant but don't get changed or consumed in the chemical reaction. Okay, so they help the reaction take place, but they are not a part of it and they're not part of the final equation or the products. Okay, so I have an example for this. Okay,
A dating one?
yeah, dating one. What's in your dating examples? Okay, so these are your reactants. Okay, we got what was the names that I said earlier? This is Bob and then Sue. Okay, thank you. Yeah, I just need two of them. Okay, this is Bob and Sue. Okay, Bob and Sue. Okay, and in order for the point of the reaction is for Bob and Sue to date. Okay, this is the end goal of the reaction. Okay, end goal of dating is marriage. Okay, so they're gonna get married, and they're holding hands. Okay, one really long finger. Okay, so this is when they're single. So this is Bob and Sue. And this is Mary. Hey, can you guys stop judging what Sue looks like, okay? Okay, everybody is beautiful in God's eyes. You're not God, but everyone's beautiful in God's eyes, okay? All right, so this is Bob and Sue. However, let's say Bob is super duper, okay, oblivious. Okay, he's dumb, as many guys are, Exhibit A, right? Super oblivious, doesn't know what's going on. Sue is texting him. Sue is talking to him in class. She wants to be lab partners, right? Whatever. But Bob's like, I don't know what's going on. Okay. Luckily, Bob has a nice friend. Okay, we'll call this one Jim, the one nobody wants. Okay. And Jim comes along and Jim tells Bob how great of a girl Sue is. It's like, Sue is a great catch. She is smart. She is pretty. She's good to her parents. And she would be great for you. And so Bob's like, hey, Jim has a great point. And then so he finally starts understanding the hints and takes that initiative to ask her out. Okay, and that's the moral of the story. Okay, the moral of the story is if you like somebody, just ask them out. Whether you're the guy or you're the girl, just ask them out. It doesn't hurt. If they say no, it's okay. You move on. Okay. Anyway, Jim is a typical wingman. Okay, and a wingman is a great example, or wingwoman is a great example of a catalyst because they help the reaction take place, but they're not part of the marriage at the very end, right? Because polygamy is illegal in the US and it's also pretty immoral, okay? Teaching morality now. Well, Mormons, they said that they had a revelation from God that polygamy is no longer allowed when they applied for statehood of Utah back in 18 something. Anyway, that's beside the point. Let's not talk about religion here. Okay, so the point is the catalyst is the one that helps the reaction take place, but is not the part of the products at the very end, right? It'd be creepy if Jim tries to get in on this marriage, right? Jim, you're a good friend and you helped us get together, but you are not part of this marriage, all right? You're not on the marriage certificate. Yes.
Wait, so for example, like
higher heat is not a catalyst. Catalysts are the compound, like they're physical compounds that take place. Yeah. It needs to be a physical molecule.
So like if it was next to it.
Yeah, they have to connect with it basically, and usually they change.
They're not reacting.
They're not reacting. It just kind of like holds on to one. There is a intermolecular force, but it doesn't combine with the molecule. So it'll use something like hydrogen bonds, dipole in order to somewhat connect to one of the reactants. Usually they change the shape of the reactant so it can react with the other one better. And then it lets go at the end. Yeah, it breaks off at the end. Yeah, exactly. Exactly. It gives you the push. It lowers the activation energy. So if we put this in the energy diagram, it would look like this. This is the regular reaction. See how that there's a huge activation energy, right? It needs a lot of energy for the reaction to take place. But the catalyst, what it does is it lowers the reaction energy, maybe puts in multiple steps, makes it easier for the reaction to take place. Yeah, but the catalyst is not part of the reaction, or it's not one of the products. There's no permanent connection at the very end. Yeah. Okay.
Like, so can you explain like this, like examples, like how would that actually work, like in a reaction?
Yeah, so we got our excuse me, we have our example reaction right here. So our reactant is hydrogen peroxide right here, okay? And it needs to turn into 2 H2Os and 1 O2, okay? But it requires a lot of energy for that to happen. And usually when we're talking about catalysts, it's one of the more common ways we look at it is in like it's like inside a cell, okay? Now inside of a cell, because cells are living, they're very delicate, right? You can't heat them up too much, right? If I throw you in an oven to make a reaction take place, not going to end up well, right? It might make the reaction go, but it'll kind of defeat the purpose of the cell. You can't increase the concentration too much because then you'll throw off other balances that need to be in the cell. So in order for biological systems or cells to make these reactions take place without changing the temperature, without changing the concentration, what they do is they employ catalysts. So here, some of the catalysts, the catalyst is Br minus and H plus, and it allows the reaction to take place without meeting this insanely high energy requirement. And then if you guys notice at the very end, it produces H2 and O2, but the Br minus and the H plus are still kind of just hanging out by itself. They're not part of the final products. They just help the reaction take place, and then they dip, as a good wingman should.
Are they always higher?
Not necessarily, yeah. And a lot of times they're really big molecules, like a lot of proteins in your body. Enzymes, you guys might have heard that term in biology. Enzymes are catalysts, but they're enormous molecules. Yeah. No, oxytocin is something else. That's a hormone, yeah. A big molecule like oxytocin, even bigger. Yeah, some of these are like tens of thousands of AMU. Yeah, that's actually a big reason why your DNA is so important. Your body uses DNA to make proteins. A lot of these proteins are there to help your cell do certain things, lower the activation energy. That's why if your DNA gets messed up, it can kill you or cause cancer or screw you up because your body is no longer able to overcome these activation energies to have the vital reactions for life. Yeah, it's a very delicate process. You are very delicate. Yes.
So are those like intermediates?
No, they produce intermediates. So when they are connected to the reactants, you can consider that an intermediate. So they connect to the reactant, they help it react, but then while it's helping it, that would be your intermediate because it no longer exists at the end. They break off at the very end. Yeah. Your intermediate is that reactant catalyst complex. That's what they call it.
If the blue, like what happens within the equation? So like
The blue is all the stuff that is working in the equation, but the red is the overall reaction. Yeah. Mhm.
So it's the overall equation always like analyzed.
Yeah. Mhm. It does not include the catalyst. You don't write the catalyst in the overall reaction. Yeah. Good question. All right. Make sense? Yes. Catalysts just help speed up the reaction. Okay. All right, so with that being said, let us go into 2 practice problems and then we will finish up. And I think we might be able to finish today. Okay, 11.22. Okay, so I got these models here for you, these pictures for you. Sorry, I didn't draw them. They could have been more beautiful. Okay, but there's a 2-step mechanism for the destruction of ozone in the upper atmosphere. I want you guys to identify the reactants, the intermediates, the catalysts, and the products, okay? And you can just write blue dots or just draw it, right? White dot, whatever, yeah. No, that's just different examples of catalysts. So like C is the one I was talking about, enzymes, right? They accelerate their proteins usually. And there's different types of catalysts.
Are the catalysts always intermediates?
They form intermediates, yeah.
I think is like the catalyst, like, that's what the equation's called, or the catalyst, like, the actual.
Catalyst is the actual compound that helps speed up the reaction.
Okay.
Yeah.
So, is the catalyst the intermediate?
When the catalyst connects with one of the reactants, that forms the intermediate. I'll go over this problem in a sec. Yeah. Just try at least to identify the reactant and the product. Alrighty, guys. So if you guys are finishing up, please feel free to finish up and just check with me, but I'm gonna start going over the answer. Okay, so let's start with the reactants. Okay, so I think the easiest way to, I guess, understand this is by figuring out what chemicals you start with in the equation. Okay, so out of the, I guess you guys can describe it to me. What does the reactant look like? Which molecule is the reactant? Yeah, the three thing, right? This right here. This would be your reactants. Okay, so I'll just put it as R. Dang it, that color. R. Okay, that's your reactant. That's what you start off with. Okay, and then let's think about what is made. Which compound is made in the reaction? So how many blue? Okay, it is blue dots. Yeah, not the three, because the three is the reactant. Oh, yes. You're right. Yeah, the product, the double dot ones. Okay, because that's what's made. Okay, you start off with the triple thingy, and then you end up with the products. Okay. All right. Now, catalysts, the easiest way to identify it is they look the same in the beginning and at the end. So which one of them is the catalyst? Yeah, the white dot, the white single dot. So this is the catalyst. Because if you notice, there's a white circle in the beginning and a white circle at the end. It hasn't changed, right, in the reaction. It gets used, but it doesn't change itself. So that's the catalyst. Yes, used and abused. Okay, now the intermediate, remember, is when the catalyst bonds with the reactant. So this would be, or it's something that's used, but then not present at the very end. So this right here would be your intermediate. Okay. The catalyst is the thing that looks the same in the beginning and at the very end. So it gets used, right? The catalyst bonds with one of the blue circles, but then it detaches, and at the very end, it's just a white circle again. It's exactly the same as when it started. Yes. Yeah, the reactant is the three blue circles. Okay. Okay, now, one thing I do want you guys to be aware of is that in these problems, especially if you ever see the term if any, it means that it might not have all of the things above. Okay, obviously every single equation is going to have a reactant and product, but you might be missing either a catalyst, you might be missing an intermediate. So just keep that in mind, okay? And that's my hint for the next question. But before we move on, do you guys have any questions about this one? Okay, all right. So this is one more tangible, and this is the last question before we go into the last section of this unit. I know. Okay, I want you guys for this two-step mechanism, identify the reactant, the intermediates, catalysts, and products, if any, and see if you can write the overall reaction. Okay. Okay, so we have our two-step mechanism here. So let's start by identifying the reactants. So what is one of the reactants in this equation? Yeah, NO is the thing that we start with. Do we have any other reactants? Yeah, H2. So we got the H2s. Good. All right, let's look at the product, because I think that's the easiest. What are the products? Yeah, there you go. Good job, guys. Any intermediates?
Yes.
Yeah, so too. Any catalysts? No. Good job, guys. So yeah, I guess my hint hopefully was helpful. If they ever say if any, you might not have all of them. Okay, overall reaction should be pretty easy. Just get rid of the intermediates, and then you can just put everything together. So you got 2NO plus 2H2, and that produces N2 and 2H2O. Easy way to see if you got the correct overall reaction. It should be balanced at the end of it. Okay. Any questions? All right, guys, you guys ready for the end?
Yep.
Yay. Okay. Last thing. What? Yeah, that's what I'm trying. Okay, so last thing we're gonna talk about is something called steady step approximation. Now that already sounds irritating, right? A steady step approximation. Okay, now you guys don't need to write the full definition down. I'm just gonna summarize it for you, okay? Or actually, we're gonna look at an example, and that's gonna allow us to understand what steady step approximation is, okay? So we got this reaction right here. We got the steps, okay? Now, if you guys take a look at the steps and let's say, hey, we want to write the rate law, okay? It might be very tempting for us to just say, hey, the rate is gonna be equal to the slowest step, right? So here you go, K, concentration of NO2, F2, done, right? That's usually what you would think. However, if you take a look at this reaction, you're going to notice that NO2F2 is an intermediate. Do you guys see that? It's produced and then used up and not at the very end. Okay, unfortunately, we cannot use intermediates for the rate law. Okay, so let's write that down somewhere, okay? Ooh, what is that? Okay, no intermediates for rate laws, okay, of overall reaction. So if you write the rate law using the slowest step, but the slowest step has a intermediate, you can't use the intermediate.
So you have to use the second slowest step?
No, you have to calculate what it is. I know. You gotta do some maths.
Why is it?
Because I love you guys very much. We can't use the intermediates because you can't measure the concentration of an intermediate. Yeah, experimentally, because it's used up, so we can't concentrate.
What if you measured it in bottles?
You can't. You can't.
What if you were just that good?
Physically impossible. You are not that good.
What if I was?
No human is that. If you could find the methodology to do that, you would probably win a Nobel Prize. If you could find the concentration of intermediates within like, because these reactions, you gotta remember, some of them take place in like less than a millisecond. So if you could find a way to, yeah, some of them take, okay, for those ones, yeah, sure. But that's not what we're talking about here. They're not very useful for studying in a lab if it takes millions of years. Okay, so okay, so let's figure out how we can figure out the overall rate. Okay, now we got to use some fancy thinking to figure out what the overall or the rate is if it's intermediate. Now, one thing we do know is that this is going to determine the rate of the reaction, right? This determines the rate because it's the rate determining step. Okay, it's the RDS. So we got to figure out what the rate of this is and then find a way to describe it using the reactants and the products. Okay, so one thing that you guys might remember from before is that the forward rate is always equal to the reverse rate. You guys remember that? The forward rate is always equal to the reverse rate. Reactions are reversible. A lot of times they are. Okay. Which means going from step 1 to step 2 is the same as rate as going from step 2 to step 1, right? It's just the opposite. Okay, so let's we can use that information to derive another equation, okay? So the forward rate, okay, the forward rate is going to, oh, actually, I'm not going to write it like that. I'm going to draw arrows. Okay, so the forward rate right here, going from step 1 to step 2, the rate of step 1 to step 2 is, I'm going to do K1 because each of these steps has its own rate constant. It's going to be the concentration of NO2 times the concentration of F2. Okay. Okay, and that is equal to the reverse rate, so the K reverse of the second step, NO2 F2. Okay, and it's getting a little bit super mathematical now, so please stop me if you guys have any questions. But step 1 going to step 2 is the same as step 2 going back to step 1, so the reverse K. Make sense? Okay. Now, what we want to figure out here is we want to find out the K overall. Okay, the K for the overall reaction, because the reaction itself overall has its own rate constant. Okay, so what we're gonna do is we want to isolate this concentration right here, because we know that the rate is determined by the slowest step. The slowest step has a rate that is equal to this right here. Right, so if you can figure out what the concentration of this intermediate is, you can figure out what the rate of the reaction is. Okay, so basically you're solving for a missing variable. You're solving for this right here. Yes. No, it's not equal to that. It would be, I guess you could say the reverse of the third step is equal to the second step. Basically, we're just trying to solve for the concentration of NO2F2 by using this relationship. The rate forward is equal to the rate reverse. That way we can just plug it in here, because we know already that this is the slowest step. And if we can figure this out, then we can figure out what the overall rate is. Make sense? Okay. Okay, so what we're going to do is we're going to solve for this variable right here. So just simple math, we can just divide by K reverse, and that's going to give us the concentration of our intermediate. Yes.
Why is, I already said,
No, you're good.
why is the arrow?
Oh, because the rate going from step 1 to step 2 is equal to the rate going backward from step 2 to step 1.
What does the arrow?
Rate determining step.
The arrow, the reaction, like.
This right here?
No, the like between the actual reaction, like the.
Mm-hmm.
Oh, the one in the middle. Why is it the arrow like?
Oh, because it's a reversible reaction. It's a reversible reaction. Don't worry, it's not that important. Yeah. We're gonna get to what that means in the next unit. But for now, just know that it means the reaction can go backwards and forwards.
But it's not like, so I thought the reverse reaction, it's a different speed. I thought it was the opposite. But it's like that with the arrow.
Yeah, so and that's why we use the K reverse. K reverse.
It is a different speed.
It is, so step 1 and step 2 have a different speed.
Yeah.
But their relationship is equal to each other. The forward reaction going from 1 to 2 is the same as 2 going to 1 reverse. So does that make sense or not?
A little bit.
So let's go backwards and go over it, okay? So we know that there is a certain speed it takes to go from step 1 to step 2, right? Yes?
Yes.
Okay, it goes at a certain speed. So let's just say for example, it's 1 molarity per second. Okay. Going backwards is the same thing. It's 1 molarity per second if we multiply it by the reverse K, the rate constant, right? So this, if the rate constant times the concentration or the molarity per second is the same as going backwards. That's why we set up this relationship right here.
So it becomes the same because of the constant.
Yeah, because of the constant. They share the same constant in between the two.
Okay.
Yeah. Okay, so what we're gonna do now is we're gonna plug in what we have here into the rate law. So the rate law for the overall reaction is K times all this stuff right here. It's gonna be K1 NO2 F2 divided by the reverse K. Okay, all we're doing is taking this right here and replacing NO2 F2 with what we isolated. Okay, we're just doing some algebra here.
Would that be like?
No, because do you know what the K reverses? No, right? Okay, so far so good. Okay, so what we're, oh, sorry. Oh, and sorry, this is gonna be K2 also, sorry, my bad. I forgot to add this, but again, it's the K value for step 2, so this should be K2, my bad. Okay, and so what we're gonna do here is we're going to write the rate like this. We're gonna write the rate, and we're gonna write the rate is K overall times the concentration of NO2 times the concentration of F2. And this will be the rate law for the overall reaction. And we'll do this with the understanding that K overall is equal to the rate constant for step 2 times K1 divided by K reverse of 1. Okay, this is the understanding that we need to have. Okay, so basically, if we plug in numbers, K1 is going to be, we said it was 1 molarity per second, right? Whatever K follows step 1 to step 2, and then the opposite for the reverse reaction. Okay. You guys look very lost. Yeah, it's a lot of algebra. We're taking from the constants of the between the two steps. Okay. So if I simplify what these variables mean, okay. K reverse, I think that's probably the one that's most complicated, but it's basically the K of the reverse reaction of step 2. Okay, basically what's the K to go backwards in step 2? Because every reaction is reversible, right? It can go forwards and backwards. And so it's the K value for that step. Okay.
Can that say stop?
Step. All right. So we're gonna go over a problem together just to make sure that we are on the same page before we finish up the unit, okay? And we'll do more practice problems with this stuff next time that we meet. Yes. Of the what's the rate of the reaction? What's the rate law? This right here. This is the rate law. And then we recognize that K is K2 times K1 divided by K reverse. Okay. Okay, let's do a practice problem real quick and then we will finish up together. All right. Okay, and I have all the stuff written down here if you guys want to take a look at the math on your own time. And I labeled all but this is the answer. This is the rate law for the reaction. Yeah, we this thing right here, that we simplify it as K overall because nobody wants to write that whole thing. So I wrote it right here. K overall is equal to K2 times K forward divided by K reverse. Yeah. So we're just simplifying the variable. Okay, I'll show you guys how to use it right here, and then I'll let you guys go. Okay, so we're gonna write the expected rate law for the overall reaction. Okay. Now, we know that just based on this right here, I don't know what that is. Okay, we know that the slowest step is going to determine the rate, right? The rate is equal to K2 times the concentration of NOBr2, but NOBr2 is a intermediate, yeah.
Ask you to do it next time.
Yeah.
Is it 1 minute? It's 2 minutes. Okay, we'll do it next time. I just wanted to finish it today. All right, you guys can start packing up. You guys can plug your Chromebooks in and put your chairs up. I would appreciate it, and we will do it next time.